Have you ever written a piece of code, something that looked totally simple, but it just acted weird in a way you couldn't explain? Well, that happens to everyone. And a lot of the time, the answer is hiding in how your program is actually using memory. So today, we're going to pull back the curtain and see what's really going on with two of the most important concepts in programming, the stack and the heap.
All right, let's just dive right in with a classic little programming puzzle. This code seems super straightforward, but its result is really surprising, and it reveals a fundamental secret about how languages like Kotlin, Java, and many others handle their data.
So here's the setup. It's really simple. First, we make a new car object, and we say its color is blue. We'll call that car1. Then, we create a second variable, car2, and we just set it equal to car1. And for the final step, we take car2 and change its color to red. Okay, so here's the million-dollar question. What color is car1 now? I mean, your first instinct is probably to say blue, right? We only touched car2. We never touched car1 again. But when you actually run this code, the answer that prints out is red. So what is going on here? How is that even possible? Well, to solve this little mystery, we have to put on our detective hats and go investigate our program's memory.
So, our first stop is the big picture. Anytime you run a program, your computer sets aside a special area of memory just for it. Think of it like a private digital workspace. But this workspace isn't just some big, messy pile. It's actually a very neatly organized map.
You know, pretty much every modern computer is built on an idea called the von Neumann architecture. And the key concept here, the big takeaway, is that your actual code, the instructions, and the data that your code is working with, well, they both live together in the same shared memory space.
And like I said, this memory map is organized. It's got different neighborhoods, different regions for different things, but for our car mystery, we only really need to care about two of them. You can think of them as the fast-paced downtown area called the stack, and this huge sprawling warehouse district called the heap.
These two places, the stack and the heap, are where all your data ends up living. But they work in completely different ways, and understanding their jobs, well, that's the key to cracking this whole case.
Okay, probably the best way to get a feel for them is with an analogy. The stack is kind of like a pile of sticky notes on your desk. It's super fast, right? You just slap a new note on top or pull a top one off. It's perfect for quick, temporary stuff. The heap, on the other hand, that's our giant warehouse. You can store huge, complex things there, and they can stick around for a long time. But, finding something in a massive warehouse and then putting it away again, that takes a little more effort.
So as you can see, there's a trade-off. The stack gives you crazy speed and handles all the cleanup for you automatically, but the heap gives you tons of space and flexibility for things that need to live for a while. And to make sure that warehouse, the heap, doesn't get cluttered with junk, modern languages have a cleanup crew called a garbage collector that comes through every now and then to clear out old stuff you're not using anymore. All right, we've met our suspects. We know how the stack and the heap work. So now let's go back to our original code and watch it run again. But this time, we're going to keep an eye on what's happening in both of those memory locations. Okay, here's line 1. When the computer sees val car1 equals car, color equals blue, it does two separate things. First, it goes to the heap, our big warehouse, and it builds the actual car object. There it is, with its blue color. Then, back on the stack, our quick sticky note area, it creates the variable named car1. But here's the key. Car1 doesn't actually hold the car. No. It just holds the memory address, a pointer, or a reference to where the car is located in the heap. Think of it like a claim ticket for the car in the warehouse. And right here, this next line is the moment everything clicks. When we say val car2 equals car1, we are not building a second car. Not at all. All we're doing is taking the claim ticket from car1, making a photocopy of it, and handing that copy to car2. So now we have two claim tickets, but they both point to the exact same car in the warehouse. So let's be super clear here. We have only one car object in our entire program. It's sitting there on the heap. But on our stack, we now have two different variables, car1 and car2, and they both hold a reference pointing to that one single object. So what happens when we run the line car2.color equals red? Well, the program takes the claim ticket from car2, follows it over to the warehouse, finds the object at address 0xabcd, and repaints it. It changes that one object's color property to red. And mystery solved, because now when we ask for car1.color, the program takes car1's claim ticket, follows it to the exact same object at that same address. And what color is that object now? It's red.
It turns out car 1 and car 2 were never two different cars. They were just two different names for the same thing.
Okay, so this brings up a really important question. If just using the equals sign only copies the claim ticket, how in the world do you actually make a brand new, totally separate, independent copy of the car?
Well, this is where you run into the idea of a shallow copy versus a deep copy. A shallow copy is kind of like duplicating a playlist on your music app. Sure, you get a new list, but it's just pointing to all the same song files. If you delete a song file, it disappears from both playlists. A deep copy, on the other hand, is like actually downloading a second copy of every single song. Now you have a completely separate, independent collection. Understanding this difference will save you from so many headaches. So, besides just being a fun little puzzle, why does this whole stack versus heap thing matter so much? Honestly, it's because this concept is the foundation for almost everything you do when you're writing software. If you only take one single thing away from this whole explainer, please let it be this. In languages like Kotlin, Java, Python, C#, you name it, variables don't hold the objects themselves, they hold references. They hold the address of where to find the real object out on the heap. If you can get that mental model right, everything else starts to make so much more sense. So let's just do a super quick recap. Simple little things like numbers and true-false values, we call these primitives. They live directly on the fast stack. But bigger, more complex things are objects. They always live out on the heap. The equal sign just photocopies the reference, that claim ticket. And if you actually want a new independent copy, you have to explicitly ask for one.
And that brings us to the final thought I want to leave you with. Think back through some of the code you've written. Have you ever had one of those bugs where you change something in one part of your program and then something completely unrelated seems to break or change unexpectedly? Now that you understand the difference between a value on the stack and a reference to an object on the heap, what old bug or weird behavior in your own projects does this finally explain?